Hi, welcome to part 2 on interval of convergence. Now in part 1 we learned how to find the radius of convergence, and we'll get back to that. But I want to take a moment to talk about the importance of it. We're looking for values of x that will make this series converge. Now we could randomly guess. For example, I could let's say x equal 3. Well, if I plug that in from n equals 0 to infinity, we would get 6 to the n. And if you look at this is a geometric series, but r is 6, which is greater than 1. Therefore, this series diverges. We don't want divergent, we want it to converge. But are there values for x that we can make it to converge? Of course. I can let x equal, let's say, 1/3. Well, in this case, my series from 0 to infinity would be 2/3 to the n. And in this case, r is 2/3, which is less than 1. Therefore, this will converge by our geometric series. So we can see that there are values for x that can make this converge, and that there are values for x that will make this diverge. Well, we want convergent. So to answer this, we first need to find that radius of convergence. Now, to get the radius of convergence, we use the ratio test. We took the limit as n goes to infinity of the next term. This becomes 2x to the n plus 1 divided by the original term, 2x to the n. And we set that less than 1. We had to set it less than 1 because we want this to converge, and that's what our ratio test tells us. And if I simplify this as x goes to infinity, this just becomes 2x less than 1. Now, it should be an n. Now remember, we're only interested in letting n go to infinity. Since neither one of these has an n, I can take them both out. And I get the absolute value of 2x. The absolute value is going to become very important for us, times the limit as n goes to infinity. Well, remember, there's no n, so if I factor out the 2x, we just left with 1 on the inside, is less than 1. And as this term goes to infinity, that just remains 1 the entire time. So what we're left with is the absolute value of 2x is less than 1. So remember what this is telling us. As long as the absolute value of 2x, the distance of 2x, is less than 1, this will converge. So that tells us our radius is 1. In other words, remember, my radius is 1. So if I'm starting at 0, if I go out 1 unit one way, I'm at 1. If I go out 1 unit the other way, we're at -1. So this is saying as long as 2x is between -1 and 1, our series will converge. So we have to solve this now. So what I'm going to do is I'm going to solve this. 2x less than 1 greater than -1. So we're saying x has to be between -1/2 and 1. This right here is what's called a possible, we'll talk about why that is, possible interval of convergence. Now it's an interval because what it's saying is it says convergence, give me 1 second, it's saying anything between -1/2 and 1 will guarantee to converge. That's what we set up here, 1/3 converged. Anything between -1/2 and 1 will, can't do math, and +1/2 will converge. What we need to do now is, what about the endpoint? And that's going to be step 2. So we know anything between -1/2 and 1/2 will converge. What we need to do is check the endpoint. And this is the most important part. So my first endpoint is -1/2. What I do is I just plug it into the original problem. Remember, it was 2x, right? So if I multiply 2x by -1/2, I get 2 times -1/2 to the n, which becomes 0 to infinity of just -1 to the n. Now this doesn't take too much. I mean, this is geometric, right? So we know r is, the absolute value of r is 1, so therefore this will diverge by our geometric series. So what that's telling me is that the endpoint, negative 1/2, won't work. Well, what about the other endpoint? We have to check that as well. What about x equals 1/2? Now this one's pretty obviously, it's not going to work from 0 to infinity. This becomes 2 times 1/2 to the n, which again, n equals 0 to infinity of just 1 to the n. Again, you can just geometric or nth term if you want to, right? Equals 1. Therefore, this also diverges by our geometric test, geometric series. So what's that telling us is that the endpoints don't work. So I'm going to write out my answer. My radius we found earlier was 1, and our interval is from negative 1/2 to positive 1/2. So if you go on, so let's take a look at another example here. Okay, example number 2. Let's see here. Let's try this one. Let's see. N equals 0 to infinity of x to the 5n over n factorial. So I want to try this one. So ready? The first things first, we got to find our radius. Okay. So to get the radius, we take the limit. We're going to use that nth term test. Sorry, not the nth term, the ratio test. This becomes x to the 5n plus 5. Well, this is 5 times n plus 1, right? Over n plus 1. Now, because it's the ratio test, I'm going to multiply by the reciprocal of the original. That's dividing it by the original, same thing. And I get x to the 5n, just 5n there. We know this has to be less than 1. So if I'm solving this, simplifying this now, we get the limit as n goes to infinity. What we're left with is just x to the 5th on top. And on bottom, whoop, got my factorial there. This is n plus 1 times n factorial. Those cancel. And I get over n plus 1. Now this is going to be a special case. We're going to like this one. Okay? I get a special case right here. Now, if I'm looking to see if n goes to infinity, it has to be less than 1. The x to the 5th, I can just take that out. So I get the absolute value of x to the 5th times the limit as n goes to infinity of 1 over n plus 1. This has to be less than 1. Now, something kind of cool happens. This is saying that the limit as n goes to infinity, this just goes to 0. Isn't that neat? This just goes to 0. So I'm taking x to the 5th times 0 less than 1. This is just 0 is less than 1. This is always true. 0 is always less than 1. So what is that telling us? That this series always converges. Always. Now, it does have a radius. It's going to be infinity. It even has an interval. Can't spell interval. It's from negative infinity to positive infinity. So what is it saying? No matter what you let x be, this series will always converge for us. If you let x be a billion, trillion, infinity, that will converge. That's kind of neat. Now if you go to part 3, I'm going to take a look at another interval of convergence that's going to be slightly more challenging for us, okay?